this course on fundamentals of transport processes. In the past few lectures, we have been discussing high Peclet number transport, that is where convection is dominating, flows past objects or flows through pipes and channels, or flows of films over a surface, where convection is large compared to diffusion in the limit of high Peclet number. However, close to surfaces, diffusion has to be important, because transport from a surface has to take place perpendicular to the surface only due to diffusion. There is no convection perpendicular to the surface. We had looked at what are called forced convection problems, where there is fluid flow past surfaces generated by external forces. For example, we looked at the flow past a flat plate in this problem, where we had a fluid flow past a flat surface, and that flow was prescribed for us. Similarly, we looked at the problem of a flow past a sphere, a spherical particle. Particle is stationary, the fluid is moving incident on the particle from far from the particle. And similarly, we had looked at, for example, falling film problems, where we had a falling film here with a velocity that is already determined by the gravitational acceleration, and we just had to find out what was the mass transfer. We had looked at flow due to the flow past a bubble, for example, where we had a no slip condition, a zero shear stress condition, a slip condition at the surface of the bubble. In all such cases, the disturbance due to the concentration or the temperature field was restricted to a thin region near the surface of dimension much smaller than the characteristic dimension in the problem, the pipe diameter, the particle diameter. Within this region, the convection and diffusion continue to remain in of equal magnitude in the limit as the Peclet number goes to infinity. The characteristic dimension of this region is the boundary layer thickness, and within this boundary layer, convection and diffusion are of equal magnitude. So, if I define a scaled coordinate perpendicular to the surface as the coordinate divided by the boundary layer thickness, the equation in terms of that scaled coordinate will be independent of Peclet number even as Peclet number goes to infinity. The boundary layer thickness will decrease as the Peclet number increases. For the flow past a surface with a no slip boundary condition at the surface, the boundary layer thickness decreases as Peclet number to the minus 1/3 power. We saw from the convection diffusion equation why that is so. For a surface in which there is a slip boundary condition or a zero shear stress boundary condition, the boundary layer thickness scales as Peclet number to the minus 1/2. From the equations, we saw why that is so. Similarly, the flux, which scales as the gradient of the temperature, is inversely proportional to the boundary layer thickness. So, the Nusselt number or the Sherwood number will scale as Peclet number to the plus 1/3 power for flow past surfaces with a no slip condition, and to the plus 1/2 power for flow past surfaces where there is a zero shear stress condition at the surface. Okay. And we had also looked at a Taylor dispersion problem, where in fact the dispersion coefficient scales as Peclet number square in this case. That is because the flow velocity distorts any initial concentration field that has been imposed on the problem. Okay. The last topic that I would like to go through, okay, is what is called natural convection. If I had, for example, a heated vertical flat plate, okay, or some vertical or some horizontal pipe, okay, with temperature T naught at the surface, okay, in an ambient fluid with temperature T infinity far away. Let us say that this object has a higher temperature than the ambient fluid. Okay. So, the fluid that comes into contact with this object is going to get heated up. Hot fluid has a lower density. Therefore, due to the gravitational force, the hot fluid has to flow upwards because it has a low density compared to the ambient fluid. Okay. Let us say that the ambient fluid has density rho infinity, a constant density far from the surface. The hot fluid close to the surface has a much higher density, and due to that it is going to flow upwards. Okay. And as it flows upwards, the cold fluid has to come in to compensate. Okay, the cold fluid has to come in to replace the hot fluid. So, basically the hot fluid is taking along with it the heat from the surface and transferring it upwards into the ambient, and cold fluid is coming in. That mechanism can result in a significantly higher rate of heat transport compared to thermal conduction in fluids. That is called the natural convection process. Natural because in this case the velocity field is decided by the temperature field itself. It is not determined by any imposed flow. Okay, it is determined spontaneously by the temperature field itself. Where the temperature is higher, the density is lower and the fluid rises due to buoyancy. Okay. So, because of that we have to determine the velocity scale from the difference in temperature itself. Okay. And then we have to solve equations for both the velocity field as well as the temperature field. In the previous case, for forced convection, the velocity field was specified, and therefore we just had to insert that into the convective terms in the equation for the temperature field. In this case, the velocity field is not specified. It has to come out of the equations for the momentum equation with the body force corresponding to the force density exerted by the difference in density, mass density of the difference in mass density results in a force density that is exerted on the fluid, and that results in a body force which enters into the momentum equation and which drives the velocity field. Okay. So, the equations that we would solve, in this case we will assume for the moment that the system is at steady state. The equations that we have to solve are the convection equation let me just write it in vector form here for simplicity, okay, and then I will write it in terms of components. U dot grad T is equal to alpha del square T, where alpha is the momentum diffusivity. Okay. In this case, the streamwise direction is along the surface, the cross stream direction is perpendicular to the surface. Okay. So, a natural coordinate system would be to consider this perpendicular, the cross stream coordinate as y and the streamwise coordinate as x. Okay. Or in this case, I would consider y and x at each location on the surface, depending upon the orientation of the surface. Depending on the orientation of the surface, the streamwise direction is along the surface, the cross stream direction is perpendicular to the surface. So, that is the energy conservation equation, and then I have the mass and momentum conservation equations. The mass conservation equation, as you recall, was partial rho by partial T plus del dot rho u is equal to 0. And the momentum conservation equation we had derived when we had looked at mass, energy, momentum balances. I will write down the momentum conservation equation for a compressible flow. Plus this term is the body force term. This term is the body force term, the force density due to the density at that location of the fluid, okay, and g is the direction of the acceleration due to gravity. In these figures that I have drawn on the right hand side, g will be vertically upwards because the fluid is lighter than the ambient. Okay. And since we are using a steady state assumption, these terms are both equal to 0. Okay. Now, we know that far from the object, the temperature is T infinity and the density is rho infinity. Okay. So, far from the object, okay, where there is no flow, okay. So, the hydrostatic condition far from the object has to be the velocity is 0 far from the object. Therefore, I will get 0 is equal to minus the gradient of the pressure. Okay. This is the static pressure, okay, plus rho infinity times g. Okay. Now, I can subtract out this hydrostatic equation, okay, from the actual equation, okay, to get an equation that contains only the dynamical part. Okay. So, that will be of the form rho u dot grad u is equal to minus grad of p minus p s, okay, plus mu del square u plus rho minus rho infinity into g, okay, where p minus p s, the pressure minus the static pressure is basically the dynamic pressure, okay, the difference between the pressure and the hydrostatic pressure. Okay. So, this I can write it as gradient of the dynamic pressure. Okay. And this last term on the right is the difference in the density between the location and the density at infinity far from the object. Okay. That I will write it as delta rho. Okay. So, my equation will become rho u dot grad u plus delta rho times g. The difference between the density at the surface or close to the surface and the ambient density far away. Okay. Now, in these equations, we can simplify these by making certain assumptions. Okay. The first is that in the mass conservation equation and in the inertial term in the momentum conservation equation, we neglect the change in density. Okay. We assume that, so for example, I can write this, okay, the first term here. Okay. So, this mass conservation equation can be written as divergence of rho infinity plus delta rho into u is equal to 0. Okay. And if delta rho is small compared to rho infinity, okay, if delta rho is small compared to rho infinity, I can neglect this term here, okay, and this would basically give me that rho infinity times the divergence of u is equal to 0. Okay. So, it reduces to a divergence free condition for the density itself. Okay. I can do a similar thing in the momentum conservation equation. Okay. I can write this as rho infinity plus delta rho into u dot grad u is equal to minus gradient of the dynamic pressure plus mu del square u plus delta rho times g. Okay. And once again, if delta rho is small compared to rho infinity, this can be neglected. Okay. So, basically the momentum conservation equation reduces to rho infinity into u dot grad u So, let us look at the assumptions we made here. Okay. What I have done here is, okay, I will call this as the simplified equations. the mass conservation, the temperature equation first is just u dot grad T is equal to alpha del square T. Okay. That is the convection diffusion equation at steady state for the temperature field. Okay. The equation for the mass conservation equation just reduces to the divergence of velocity is equal to 0. Okay. And the momentum conservation equations is the form rho infinity u dot grad u is equal to minus gradient of the dynamic pressure plus delta rho times g. Okay. Now, the density variation depends upon the temperature variation. Okay. The density variation depends on the temperature variation. Okay. If you assume that the density variation is small, if you assume that the density variation is small, as I have assumed in this case, that density variation can be written as a linear function of the temperature variation. Okay. This is written in the following form. Okay. Delta rho is equal to rho infinity beta times delta T, okay, where beta is what is called the thermal expansion coefficient. Okay. What does it physically mean? What this basically says is that delta rho by rho infinity is equal to beta delta T. Okay. The fractional change in density due to a change in temperature delta T, the fractional change in density is equal to this thermal expansion coefficient times delta T. Okay. Therefore, the thermal expansion coefficient has dimensions of inverse of temperature. Okay. This we are referencing to a density rho infinity far away and temperature T infinity far away. Okay. Therefore, this is basically equal to beta into T minus T infinity, okay, because we are taking the reference state far from the object, the temperature is T infinity and the density is rho infinity. So, delta T is variations from that temperature far from the object. Okay. So, therefore, the change in density is going to be equal to beta into T minus T infinity, which is beta delta T. Okay. So, with this linear approximation, okay, you can write the equation as rho infinity beta delta T times G, okay, where delta T is T minus T infinity. Okay. And rather than write u the mass conservation equation this way, I can also write this as u dot grad. Okay. Okay, because delta T and T differ only by a constant. So, when I take the gradients, those will all go to 0. Okay. So, these are what are called the Boussinesq equations. For natural convection. The assumptions that we have made here, one is in the mass conservation equation, we assume that there is no change in density. Okay. In the mass conservation equation, we assume that the density is constant. That implies that, okay, delta rho by rho is small. Okay, only then can I assume that the density is not varying in the mass conservation equation. Similar assumption has been made in the momentum conservation as well. Okay, the change in density is small compared to the density far away. Okay. I have also made further assumptions which I did not explicitly state. In these equations, the assumptions are that the viscosity and the thermal diffusivity are also independent of position or independent of temperature, because temperature is varying with positions. Therefore, we have neglected the temperature variations of the mass diffusivity as well, I am sorry, the energy diffusivity as well as the momentum diffusivity in this case. Okay. And the last assumption that I have made is this one, okay, that delta rho is equal to rho infinity beta delta T, okay, linear variation of temperature of density with temperature. Okay. This second one, this linear variation of course is valid so long as delta T by T infinity, okay, is much less than 1. So, that the temperature variation on an absolute scale where T infinity has to be the absolute temperature, okay, where the temperature variation on an absolute scale is small. Okay. What about delta rho by rho? Okay. Okay. We know that delta rho by rho is equal to beta delta T. Okay. So, beta should have dimensions of inverse of temperature. Okay. For fluids such as air for example, beta is of the order of 10 power minus 3, okay, Kelvin inverse. Okay. Okay. It is of the order of 3 into 10 power minus 3. For water for example, this beta will be of the order of 10 power minus 4 Kelvin inverse. It is of the order of 2 into 10 power minus 4 Kelvin inverse. Okay. Beta is exceedingly small both in air as well as in water at standard temperature and pressure. Okay. And therefore, even if the variation in temperature is of the order of tens to hundreds of degrees, delta rho by rho is still a small number. Okay. Because beta is such a small number, even if there is a variation of tens to hundreds of degrees in the temperature between the object and the surrounding fluid, beta times delta T or the fractional change in temperature is still small. And that is why these Boussinesq equations can be used for studying natural convection heat transfer problems. Okay. And it is also because the temperature variations are small, okay, on an absolute scale. The absolute temperature, room temperature is about 273 degrees. So, even if you increase the temperature by tens of degrees, this delta T by T infinity will still be a small number. Okay. And therefore, a linear approximation is a good one. So, because of these, we can simplify the equations to the Boussinesq equations, which are much easier to treat. Okay. Okay. So, how do we scale these equations? Okay. X can be scaled as x by L, y star is equal to y by L, okay, which implies that the scaled gradient is equal to L times the gradient. Okay. We do not yet have a scale for the velocity. Okay. In this case, the velocity scale has to emerge from the equations, because it is the driving force in the equations that is actually determining what is the velocity. Okay. So, we will just assume that to be some unknown velocity, which we will estimate, okay, as a part of the problem. Okay. We will assume that this is an unknown velocity that we will estimate as a part of the problem. Okay. T star, I can write it as T minus T infinity divided by T naught minus T infinity, okay, where T naught was the surface of the object, T infinity was far away. Okay. And the density of course is a constant. Okay. The density in this case is a constant. Okay. Rho is just equal to rho infinity. Okay. So, I can insert these into the governing equations. Okay. Now, so I will get u, okay, into T naught minus T infinity by L, this is not u, okay, the velocity scale, okay, into u star dot grad star T star, okay, is equal to alpha T naught minus T infinity by L square. Okay. Okay. So, that is the temperature, the energy balance equation. The mass conservation equation basically will reduce to u by L is equal to 0, okay, and the momentum conservation equation will be of the form rho infinity into u square by L u star dot grad u star minus 1 by L plus the final term, which is rho infinity g. I have to also scale g. I will write the acceleration due to gravity as its magnitude times a unit vector, times a unit vector in the direction of the gravitational field. So, g, the scalar g is the magnitude of the acceleration due to gravity. And this is a unit vector in the direction of the gravitational force. So, this has unit magnitude. This just helps us to separate out the scales. So, this is equal to rho g into T star g hat. I am sorry, there should be a beta as well, the thermal diffuse expansion coefficient. So, this is going to be my momentum conservation equation. I still do not know what is the velocity u. I can get that by either balancing the inertial and the body force term or the viscous and the body force term. The body force term has to be included in the balance, that is because it is this body force that is driving the velocity. So, you have to balance either the inertial and the body force terms or the viscous and the body force terms. In this case, we will balance the inertial and the body force terms, because as we shall see shortly, inertial terms are dominant in this case. Therefore, if I balance the inertial and the body force terms, I get rho u square by L is equal to rho infinity beta g and which implies that u square is equal to L beta g into T naught minus T infinity, or the velocity scale basically is equal to root of into the length scale. So, that is the scale for the velocity that I get by balancing out the inertial and the body force terms. Now, we have to go back to the equations and then calculate the dimensionless numbers based upon this scaling in that case. So, that scaling I will continue in the next lecture. We will look at the scaling, we will identify the dimensionless numbers from the magnitude of the velocity, put that in and then simplify the equations and try to look at what scalings we get for the heat flux from those equations. That I will continue in the next lecture. I will see you then.